Hey everyone, so welcome to chapter 31. This will be the first time that we will encounter an inductor and a capacitor in a circuit at the same time. Right? We'll also have a resistor thrown in there very shortly to make it an RLC circuit, but let's start out chapter 31 with just LC, right, for an LC oscillation. Notice there's no battery in any of these pictures, right? And that's on purpose. We're just talking about a closed circuit with an inductor and a capacitor. So let's start over here at picture A, okay? And let's just assume that this capacitor starts completely charged, okay? So that means that the electrical energy, right, the amount of electrical energy in the circuit is maximized, right? And that's the total amount of energy in the circuit, right? It's all in this capacitor. So it's all in the electric field denoted by those blue arrows. So that's where it starts. And what we'll do is we'll go around from picture A, B, C, all the way around to H, and then back to A. And we'll see that this creates one complete LC oscillation. Okay, so what's going on? Well, if this is the starting scenario, right, the plates are completely charged. There's the maximum potential difference between these plates, okay? There's no current flowing in this circuit, okay? Remember that when a capacitor is completely charged up, the current is zero, okay? The electric field is maximized, but the flow of charge is non-existent, okay? Now, if this is just allowed to go, in essence, the charge on the top plate will move counterclockwise in the circuit, right? So now it'll start to lose charge in the plates. And so now charge, or now current, will flow counterclockwise, denoted in picture B, okay? So thus the capacitor will start to lose energy, right? Lose charge. Its electric field magnitude will decrease, but the magnitude of the current flowing is going to increase. Thus, the current flowing through this inductor, and if you look really closely here, let's see if I can do, how am I doing this? Oh, there it is. Right there in that close-up view, in the inductor, there's an arrow down, right? So current is flowing down. That creates an induced magnetic field, right? Actually, current is flowing around those loops, right, of that solenoid, effectively. So that's inhibiting or resisting the flow of charge, right? That's what an inductor does. So because this current is increasing, right, through this inductor, that's increasing the magnetic flux and increasing the resistance to that flow of current, okay? So it doesn't completely stop the current flow, however, right? It just, inhibits it. So it continues to increase though, albeit slightly less than if it wasn't there. And the current continues around now to this side of the capacitor. Okay, so eventually over here in picture C, there is a point where the current through the inductor is maximized, right? Thus the induced magnetic field is maximized, denoted by those green loops, okay? And the capacitor that once started out completely full, completely full, has now lost all charge, right? And so that means there's the maximum current in the loop, but there's no charge and no electric field in the capacitor. So in case C, all of the energy, right, the total energy in the circuit is completely in the magnetic field of the inductor. So it's gone from being completely in the electric field to now completely in the magnetic field. The same amount, but it's just changing forms, okay? Moving on to D, the current is still counterclockwise, right? But now notice that the bottom plate of that capacitor is now at we'll say a plus potential, right? Compared to pictures A and B, the potentials are flipped, right? That's because charge has now been accruing on the bottom plate. And yes, I know it's actually free electrons that are moving, but we're sticking to the convention, right? The historical convention. So a buildup of charge means a buildup of positive voltage, okay? The magnitude of the induced magnetic field in the inductor in picture D is decreasing. And when we're over at picture E, now the capacitor has fully charged up once again, but the potential is reversed from when it started. Okay? And now again, because it's fully charged, there is no current flow. Right? So really, the current here in D was decreasing. Right? It was maximum here, it's decreasing, and now it's zero over here. Okay? So there's no induced field in the inductor over here. All of that energy is in the capacitor in picture E. Okay? And now what happens to the charges? What happens to the current? Well, you can kind of think of leading up to this point, right? Leading up to this situation, the current, right? The charges were flowing into it like that, into this bottom plate. And so once that bottom plate, which has some volume, right? You can think of there being a certain amount of spots for each of these charges to reside inside the plate, right? Or on that plate. If every one of those spots of that bottom plate is filled, as soon as that happens, the charges that are continuing to try and fill that spot are pushed back. They're repelled. There's no more spots for them. And so what effectively happens is that, well, they're repelled. They go backwards now. So effectively, there's a reverse current or a back current. And we see that here in picture F, right? So there is zero current flow at the instant this capacitor is completely charged. And anytime after that, the charges are effectively repelled and now flip direction. Now they're flowing clockwise, and we see that here in picture F. Okay? So the electric field and the charge on the plates are decreasing. This current value is increasing, as is the magnetic flux through the inductor, right? Just like what was happening, say, over here in picture B. It's the exact opposite, just the other direction. And if we look closely, let's bring it down here, we should see that arrow going up now in the inductor. Okay? Notice that I forgot to mention, in picture E, the electrical energy is the total energy, right? There's none in the magnetic field. Now they're even. There's some in the capacitor, there's some in the inductor. Right? We wait a little bit more time. The current magnitude is increasing to a maximum value through the inductor. The field is maximized. The inductance here is maximized. And there is zero charge, zero electric field on the capacitor. Right? The exact opposite of up there. Again, the current's going clockwise. And so moving on to picture H, now this current magnitude still going clockwise, but now it's decreasing in magnitude. Okay? The induced field in the inductor is decreasing, the magnetic flux is decreasing, and the charge is building up more and more on the capacitor, which is increasing the value of the electric field more and more, right? Up to, once again, a maximum at picture A. Okay, so notice from A all the way over to its opposite, right, or 1/2 of one cycle in picture E, the capacitors are both completely filled. The total energy is completely electrical in both cases, but the direction is flipped, right, over 1/2 of a complete cycle. The second half of that cycle, same thing happens, but we get back to the original state, right? So you can start on picture A and go to E. That's the same half cycle. Or, of course, you can start on picture C when the energy is completely magnetic, right, go 1/2 cycle later over to picture G, right, now the magnetic field has reversed a direction, right, current still maximized, but that is still 1/2 of a complete cycle, and then you must continue back to where you started, okay? So this is one complete LC oscillation, right? And so in this chapter, we're going to look at what happens with the values of current, with the values of the inductance, and whether or not, and how they change when we put a resistor in the circuit, okay? Because if you notice, right, you can go around and around and around however many times you want, however many cycles, and the total energy will not change, right? This is a perfect circuit, right? There's no energy loss due to heat. If you put a resistor in the circuit, that does release energy via heat, because that's what a resistor does, right? P equals I squared R. So there is energy lost in an RLC circuit. So that means over time, the total energy in that case would not be constant. But if you just had an LC circuit, it would just oscillate back and forth. Okay? Thanks for watching.